For problem number 9, we are working with a charged rod this time. The rod is positively charged and it's on a rod of length capital L. And we need to figure out what the electric field is at this position at the origin here. So since it's a positive charge and we take a small section of this rod, think of it as a point particle. Since this is a positive charge, and I'm going to call it positive dq because it's just a small piece of the entire charge, it is going to create a magnetic field that goes out of the positive and therefore in this direction here. So let me erase the path in between, and actually let me make a better horizontal line here. It's going to be a positive charge going outward, and then as I take more and more pieces of this rod, it's going to continue to stack positive charges pointing to the left. So the first thing we're going to do is always start with the electric field, and the electric field, if we take point charges, is just dE because it's small pieces of the electric field, and then our equation would be K dQ over R squared. Let me use a capital R because they do have lowercase r as a variable here. So to identify what that radius would be, since I know that capital L is the length of the rod, I'm going to make the distance, which would be the radius, lowercase l. So that's going to be my radius. And I'm going to take a portion of this distance and call it dl. It's just representing a little piece of the entire object. So substituting in the appropriate variables, K dQ over L squared, which is the distance from the charged piece all the way to the zero position. And then because we have L here, we're going to look at the fact that it is a uniformly distributed charge, and we can use the fact that linear density, charge density, is going to be equal to Q over L, or we can call it dQ over dL, which means that since it's uniformly distributed, the entire charge over the entire length is going to equal to a small piece of charge over a small piece of length. And obviously we want to substitute for dQ, so dQ is lambda dL. So let's do that substitution. And then now we've got our variables, L and dL, so we can pull out all the constants and start to integrate. I'm going to pull out the K lambda. I'm going to write the L as L to the negative 2, and then I'm going to integrate from the L expression, or the L variables, and then integrate dE. This gives us our entire electric field. K lambda is a constant. I need to figure out what my limits are. So the length of the rod itself starts at lowercase r and goes all the way out to r plus L. So when I do my integration, I end up with L to the negative 1 over negative 1. So I can just call it negative. And then from r plus L to r. And then when I do my substitution, I end up with K lambda times negative 1 over r plus L. Because of this negative, I know it's going to be a fraction, minus a negative 1 over r, and then turn that into a positive, flip it around so it looks nice. I've got K lambda is multiplied by 1 over r minus 1 over r plus L. Now, in your equation sheet, you're going to see K represented as 1 over 4 pi epsilon naught, but I am totally fine if you leave it in this expression. Actually, that's how I prefer to leave it. So this could be one version of your answer to number 9, part A. Okay. Part B is the electric force applied by the rod in a positive charge placed at the origin. So if I were to place a positive charge here, positive is going to repel a positive, and so it's going to follow the path of the electric field. I know this isn't part of the problem. Just to extend your knowledge, if it was a negative charge, it would actually attract the rod, or the rod would attract the charge and it would approach the rod. So in this case, it's repelling, and so we are going to have an electric force. This is part B, which is equal to electric field times the positive charge. And we know the electric field is K lambda times 1 over R minus 1 over R plus L. And then we're going to multiply that by Q. So I'm going to multiply the Q first and then plug in the rest of the expression. So this is going to be the electric force. That is pretty simple. Okay. The last problem, part C, asks the charge will move to the left with an increasing the charge is released from the origin. Describe its motion. Since we've got a force and F is equal to ma, we know that the object is going to have an acceleration to the left. But we also know that as it moves further and further away from the charged rod, the force is going to decrease and therefore the acceleration is going to decrease. So when we want to describe this motion, we're going to describe it as move to the left with high acceleration and increasing velocity, because the acceleration is going to be in the same direction as the force, so its velocity is going to increase, but decrease acceleration over time, because we know that the electric force decreases as the distance decreases. Acceleration will therefore do the same. And so the charged particle is still going to increase velocity. It's just going to increase velocity at a smaller and smaller rate. So that's what I mean by decreasing its acceleration but increasing velocity.